All right, so we did not have a chance to do all this cone problem in class. We barely even had a chance to start talking about it, but I know that we need this information, and I wanted to make a video so that you'd have something to look at for reference and to learn from. And you can ask some questions about this in recitation, as well as we'll try to do a quick recap on Friday in class. Otherwise, let's listen to me talk about this question and watch me do some of the thinking and work that we need to do to get this figured out. So what we're going to do is pump water out of a tank. We have the acceleration due to gravity, we have the density of water, we have all of our diagram labeled with the radius being 7 meters, the height being 10 meters, and the depth being 8 meters. So what we need to do is figure out a couple of things. We need to give ourselves a coordinate axis so that we can start setting up our question. I'm going to use that the top of the tank is where x is equal to 0. The positive x direction is downward because that's what our book is doing. So I want to stick with that. And then we can label a couple of things on our axis. The first is that the water level is then at x equals 2 and the bottom of the tank is at x equals 10. All right, so we have our coordinate axis set up for us. Now what we can do next is think about some place in between. At some xk, we'll have some slice of water, and it has some little thickness, delta x, and we need to think about the volume of that piece, vk. Now, it is a circle with some thickness, delta x. So if we could figure out whatever that radius is, then we can find the volume, because it would be pi r squared delta x. Okay, well, how do we figure out that radius? Because it will be different. It's going to be much bigger up here at, say, the top of the water level and much smaller down at the bottom of the cone. So we need to use some other information about that shape to help us get a relationship between the overall shape of the cone and what that radius will be. One of the ways that we can do this is to use similar triangles. That's the method that I'm going to share here. There are other methods. I think similar triangles is a reasonable one to use. So if instead of drawing the whole cone, I just draw the triangle that sort of looks like that, and is just sort of the shadow or the cross-section of that cone, then what we can do is make a vertical piece that comes down from the center, hopefully something like that, and we know that that side length there is 7, this side length here is 10, and so if we go to some other place where we wanted a radius, and I'll color that in pink, that's r, what we'd like to know is what is r. Now some other pieces that I need to label in this triangle, so let me zoom in a little bit so we can see a little better, is that this top distance here was xk, or just x, which makes this distance down here 10 minus x, or xk, because we had the total being 10. So if this top piece is x, or xk distance, then this is a 10 minus x distance. So what this gives us is the ability to use the idea of similar triangles, which means the 7 over 10, the ratio of this side of the triangle, the big triangle, to this side of the big triangle. And that triangle that I'm talking about is, I'll overlay in blue, is this triangle here. So 7 over 10 we're getting from that triangle. Whoopsie daisy. The other side of this equation that we're going to make comes from the 7 being the same side that corresponds to the side length r in this smaller triangle. That smaller triangle I will draw, try to outline in orange on the inside. And that's what this side of our similar triangles is coming from. So the height of that smaller triangle is 10 minus x. And I'm going to use x and not xk so that we get our function for the radius in terms of x. So if we solve for r, we'll get a function for the radius in terms of x. So we can solve for r. We can multiply both sides by 10 minus x. So we'd have 7 over 10 times 10 minus x equals r. Now that we have r, we can finish finding that volume of a piece. The volume of a piece, whoa, something's going wonky there. But the volume of a piece is pi times r squared, which is 7 over 10 times 10 minus x, that whole quantity squared, times delta x. Okay, so now that we have that, the last thing that we need to do before we can set up our integral is figure out what is that distance that our slice of water needs to move to get out of the tank. So we take the larger thing minus the smaller thing. So our distance, d of x, is equal to x minus 0, which is just x. So our work integral, if we're going to pump everything out of the cone, I think, was that what it said, or what did it want? It wants us to pump everything out of the cone. So we want to pump all the water out. So we're going to integrate from 2 to 10, because that's the interval where all of the water is. We're going to start at the top, pump all that water out, all the way down till it's drained. Then we have our mass density of water, 1,000 kilograms per meters cubed. We have the acceleration due to gravity, the 9.8 meters per second squared. We have the volume, pi times the quantity 7 over 10 times the quantity 10 minus x, those two things squared. We have the distance function, which is x, and then our delta x is a dx. So that delta x becomes a dx. So there is setting up our cone problem. I'm not going to go through computing the integral. I just wanted to help us get to the point that we could set up that cone problem. I used what is the textbook standard orientation for putting x at the top of the container and the positive x direction going down. We used similar triangles to help us find a function for the radius of a particular slice. There are other methods beyond similar triangles, but that's the one that is in this video. I hope this helps a little bit. We'll have a bit more time in recitation to talk about this and another bit of time to talk in the next class. See you then.